How you doing? What do you do?
I work in
I'm Paul.
Doing anything special on the university class? Hi, my name is Suzanne.
I'm Saul. I'm a mathematician.
Wow, I could never do math.
You wouldn't believe how often I hear that at parties.
There's a lot of community.
lawyers drawing
I'm Saul Garfunkel. I'm a mathematician.
Oh, I didn't know anybody did math after high school.
But you know, Neil Simon, musical.
I'm Saul Garfunkel.
Oh, hello. I'm Jill. I'm a writer. What do you do?
I'm a mathematician.
Oh, how interesting. Excuse me.
16 years.
Day of absence. Day of absence.
Terrific.
And this is outside the rectory.
Hi, I'm Saul Garfunkel, and I'm a mathematician. I guess that you figured that out by now. I'm also your host for this series. What you just overheard happens to me all the time. When I tell people what I do, they proudly tell me that they were never any good at math. I mean, how can people feel fine about tax return, full of details and warnings, but short on explanations? No talk about why the rules are the way they are. Well, we're going to do things differently in this series. We'll devote a lot of our time to understanding the major concepts of college algebra, seeing why the techniques are useful, where they come from, and how logically they're related. And we'll also take off from here to see people in a wide range of settings use algebra to solve actual problems. Stick around.
Annenberg Media.
Okay, now that's out of the way. You've just seen the answers to all the problems that we tackle in this series. We're not particularly interested in doing arithmetic. This series is about understanding, about getting hold of the basic concepts of college algebra and learning how to apply them in ways that make sense.
An aged monk decides to make a sentimental visit to his former dwelling, the palace on the top of the mountain. He leaves his monastery at noon, slowly trudges the many steps up the steep trail, and arrives, exhausted, at 7 o'clock that night. Then he's treated to a refreshing bath, enlightening conversation, and whatever else monks enjoy when they visit a palace. So by the next morning, he feels like a new man. He sets out again at noon, walks briskly downhill, and reaches his monastery at 3 in the afternoon. Here's the question. Is there any point on the trail that the monk passes at the same time of day, going down as he did going up?
Now, you might try to work this out with numbers, maybe even set up some kind of equation to represent the two trips. We're going to learn ways of doing just that for other problems in the rest of this series. But the better approach here is to back away from the specifics of the problem. Then the whole picture becomes much clearer. Here, take a look. Let's say that this is the monastery down here, and up here is the palace. Here's the path. Well, just imagine that the trip is made by two people going in opposite directions at the same time. In other words, one leaves from here, and another one leaves from here at noon on the same day. Well, from the sketch, you can see that there has to be a point where their paths cross. He's coming down, he's coming up, bingo. So even on different days, there must be some point the monk reaches at the same time. One of the main things we'll learn from studying algebra is a useful way to analyze problems. The point of the monk story is that you can only get the answer by thinking differently, playing the problem through in various ways until you see a solution emerge. And that, in turn, is one of the real pleasures you'll discover in learning algebra. It sharpens your mind in a way that'll help you solve almost any kind of problem, even problems that have no numbers at all. Are there any other reasons to study algebra? Since you're watching this program, and quite possibly enrolled in a college course along with it, you've probably got your own answers to that question. Let me show you some of the ways that we thought about addressing it.
Why study algebra? Cut 1.
There are so many people I want to thank. I'm not sure where to begin. There's my co-star, of course, my director, and all the people who gave so much to this picture. Oh, and somewhere out there is the person that I really owe it all to. Miss Simpson, wherever you are, thanks for those unforgettable algebra lessons.
Why study algebra? Cut 2.
When I'm out here on the field, listening to the roar of the crowd, and thinking about how I'm going to spend that next $1 million paycheck, I realize that I owe it all to studying mathematics. So get smart. Take algebra.
Why study algebra? Cut 3.
Yes, join the Algebra Club, and you too will find new interests and new friends for our free booklet, The Success Equation. Call 1-800-ALGEBRA. That's 1-800-ALGEBRA. And hey, I'm not just the Algebra Club president, I'm also a member. Well, so much for hype. You know as well as I do that learning algebra won't necessarily make you famous, rich, or popular. But as we'll discover, there are deeper reasons why algebra is worth knowing. It gives you power, it tells you surprising things about the world, and it makes sense of things that are important to understand. One reason that algebra can seem forbidding is the symbols, all those X's and Y's. Sometimes it may even feel like mathematicians dream up schemes to make understanding mathematics harder than it needs to be. Actually, of course, we all use symbols every day. What does COW mean? A word is just a symbol for the thing, much like this, but easier to carry around. And here's one of my own favorite symbols, the $sign. No one would want to write out dollars 100% of the time. Now, we begin learning mathematical symbols almost as soon as we learn to print the alphabet. The Arabic numerals we use are themselves just symbols representing quantities. We don't stop to notice that the numerals 100 used this way are very abstract symbols that stand for the quantity 100. Okay, the Arabic numerals from 0 to 9, plus a few symbols like, well, plus, are all we need to do arithmetic. What do we gain by using symbols like X and Y in order to do algebra? First of all, algebra turns out to be a convenient and efficient tool for everyday use. The telephone company, for example, tells you that a long-distance call costs $2.50 for the first 3 minutes and 70 cents a minute after that. You don't expect them to list every possible length for a phone call and the corresponding price. Instead, they've given you an algebraic recipe that allows you to calculate the cost of any particular call. This is a simple example of how algebra gives you power. You're doing algebra every time you figure out the tip in a restaurant or the postage on a package. In short, every time you use a compact, general formula that takes the place of a long list of numbers. But you can do more than that. Once you have a general expression, you can manipulate it to find out whatever you don't know. For instance, if you travel at a certain speed for a given amount of time, you'll cover so much distance. Using some self-explanatory algebraic symbols, we can write that as D equals R times T. Well, what if you're driving along at 50 miles per hour and your next stop is 200 miles away? It's algebra that teaches us that we can rearrange this equation into t equals d divided by r, the form that we need to answer the question, how long will it take to get there? Now suppose the next stop is not down the road, but out in space. Our whole space program depends on being able to calculate how much power a rocket needs to escape the pull of the Earth's gravity. We couldn't afford to learn that through trial and error. Rockets are just too expensive. Here's a case where algebra is an essential tool for helping us understand something deep and important. And that gives me a chance to make one last point about symbols and algebra. By using symbols to represent the forces of nature and playing around within the rules of algebra, scientists discovered and solved the liftoff problem long before technology enabled us to think about launching rockets as a practical goal. That's an example of how algebra can be surprising. And I'm certain that right now, out there somewhere, a mathematician is working on what she considers a completely abstract problem, but her results will turn out to solve some practical problem a decade or a century from now.
So when what's-his-name said that business about that thing, she got really angry.
Well, yeah, I can understand that.
It's amazing how well we get by in everyday conversation without being very clear. Gestures and emphasis convey a lot of our meaning. If you saw your own spoken words in print, you'd often find them ambiguous. Their meaning wouldn't be certain. When it comes to algebra, well, the good news is that algebra, like all the rest of mathematics, is unambiguous. The bad news is that the world doesn't speak algebra. That means that we'll have to learn how to create precise mathematical statements from the very imprecise language in which real problems come packaged.
That one cost $5. Twice the price and only half as good.
So what you're saying is 2x equals 0.5y.
You be the ump. With runners on first and third, a batted ball hits the umpire before it gets picked up by a fielder. Is the runner on third allowed to score? You be the ump. When a ball hits an umpire before reaching a fielder, the batter gets a hit. But if you said a runner must go back to third, you made the right call.
Games wouldn't be games without rules. In fact, if you ask me to define the game of baseball, I'm going to end up telling you the rules. There would distinguish baseball from just playing catch. And the same thing is true for algebra. Rules are essential. Sometimes their function is to make mathematics consistent. Just as in baseball, we want the overall game to make sense and to be fair. Here's an example like that from algebra. We learned back in arithmetic that a square root is the number which multiplied by itself produces the original number. That's a long-winded way of saying something that we can represent much more efficiently with algebraic symbols as the square root of n equals a. We can translate this as a times a equals n. But then it's also true that negative a times negative a equals n. In other words, a number has two square roots, one positive and one negative. The square roots of 36 are therefore positive 6 and negative 6. But what about the square root of a negative number? Since a positive number times a positive number is positive, and a negative times a negative is positive, there's no number that fits our definition of square root for a negative number. Yet it's perfectly possible for a practical problem to lead to an equation like x equals the square root of negative 1. In fact, electrical engineers encounter this sort of thing all the time, because calculations involving alternating current, the kind of electricity that powers all of our household appliances, have to represent a voltage that's constantly flipping back and forth from positive to negative. Well, looking for the square root of a negative number like this created big problems for mathematicians who faced the seemingly impossible challenge: keep algebra useful and at the same time keep the rules for multiplication and square roots consistent. As we'll see in a subsequent program, solving that one took a long time, a lot of imagination, and the creation of some new rules. The bottom line is that the rules are there for a reason, or actually for two reasons. They make algebra reliable or consistent, and they make it more useful. It's the same whether the game you're playing is algebra or baseball. The rules are the way they are because these rules define the most interesting games. In this series, we're going to see how real people use algebra to solve a wide variety of real problems. Here are just a few of the examples we'll encounter.
Michael has a kidney stone, a painful ailment that's going to require surgery. But thanks to this device, a shock generator, the surgeon won't need a scalpel. The stone is lodged here, in Michael's kidney. His doctors want to put the stone and the shock generator at the two focal points of an ellipse. Then the algebra comes into play. All the shock waves are reflected from one focus to the other, concentrating their energy on the stone.
All right, we're going to try a test shock wave now.
You're the best. I have my faith in you. I'm not worried.
Beautiful.
The shocks look and sound quite dramatic, but Michael stays awake while his kidney stone is shattered into harmless pieces. The only discomfort he feels is the noise.
We can treat patients with kidney stones, and even those with gallstones, in a pain-free and an effective fashion without open surgery.
A carefree white-tailed deer. In pioneer days, natural predators kept the deer population in check. Then we disrupted the balance by killing the predators. Ironically, that makes hunting a necessary part of today's wildlife policy.
Hunting is the most important management tool that we have to control the exponential rate of increase of a deer population.
Here's the uncontrolled population explosion in a deer herd. Hunting can limit this growth to lower levels. A 6% rate of increase avoids ecological crisis. Hunting is a treasured sport for some, a cruel and immoral act for others. But until natural predators are restored, we will have to protect the deer from themselves.
Flight 536, this is dispatch. I have had some reports of some turbulence.
Every day, an airline faces new versions of old problems: weather, maintenance, and traffic.
The thing is, if Boston starts to jam up, then, New York and all that.
To make a profit despite changing conditions, airlines like Northwest rely on algebra.
Minimizing cost is the underlying goal of any operational system at Northwest. Minimizing cost of pilot time, minimizing time that a jet engine is running on a taxiway and burning fuel. We take a look at the business problem, translate it into a mathematical function to come up with the best solution.
This lonely sentinel is a listening post, monitoring the heavens for messages from intelligent beings. Harvard physicist Paul Horowitz is conducting this patient search. The huge antenna dish collects radio waves and sends them to a bank of computers where algebraic filters sort out signals from the cosmic noise. In this second-grade classroom, a turtle is helping kids understand important mathematical ideas. As Tatiana has discovered, it's not a real turtle, it's a screen turtle that runs on a computer language called Logo.
You put a number, like 10. You'll move 10 spaces.
The relationship between a computer command and the turtle's on-screen action is determined by algebra.
20.
And if Tatiana has trouble choosing the right command, she's encouraged to act out the algebra herself.
FD 20.
Mail. It comes in all shapes and sizes, but mainly it just keeps on coming. Letters go here or there, by truck or by air. At each stage, a decision is made, and algebra helps keep down the cost. The thrill of sailing for a skipper in a brisk wind is pushing a boat to the limit of speed. The thrill of sailing for a naval architect is designing a new sailboat that can go even faster. To do that, you need algebra.
The longer the boat, the faster it will go. And this is a linear function.
It takes skilled craftsmen and the right materials to transform the blueprint into a boat. You don't have to travel far to find the applications of algebra. On land, in the air, and at sea, they're all around us.
Boy, is it cold outside.
How cold is it?
Actually, the temperature isn't so bad, but with the wind, it's brutal. What I mean is that the thermometer says 28 degrees Fahrenheit, but it feels a lot colder. So, how cold does it feel? The answer to that is what we call wind chill. What better place to study wind chill than Antarctica? And this is where researchers working for the U.S. Army came to conduct the first wind chill experiments. They measured the rate at which a cylinder of water would freeze at various temperatures and wind speeds. Let's take a look at what they found. We're going to build up a graph. On this axis, we'll put temperature running from low to high. On a second axis, we'll measure wind speed from slow to fast. Now, we still have another variable to chart, the rate of freezing. So our graph is going to be three-dimensional, with wind speed running back into the screen. Then I can put the rate of freezing or heat loss on the vertical axis, rising from slow to fast. Now, don't worry about the details of this graph or any of the calculations I'm about to do here. This is the kind of material we're going to cover in the rest of the series. When we plot the Army researchers' measurements on this graph, we end up with a surface. Every point on this surface represents the rate of heat loss for a given temperature and a given wind speed. Here's the rate of heat loss for a low temperature and a moderate wind speed. And here's the rate for a moderate temperature and a fast wind. This region of the graph represents the fastest rate of heat loss when the temperature is low and the wind speed is high. And now, the moment you've been waiting for. We can describe this graph with an algebraic equation. Aha! Symbols again. But here their meaning is pretty straightforward. V is the wind speed in meters per second, T is the air temperature in degrees Celsius, and H is what's called heat loss, measured in complicated units you don't want to hear about. Essentially, H describes the amount of heat you'd lose from a square meter of your skin if you were outside for an hour. So this equation summarizes the original observations made near the South Pole and gives us a way to predict heat loss by plugging in different values for wind speed and temperature. Okay, now I'm going to skip over a step, even though I hate to pass it up since it's algebra. The effect is to convert all these uncomfortable units to good old degrees Fahrenheit and miles per hour. But we're still calculating heat loss, and that's a bit abstract. What I'd really like is a number that's easier to understand, a number that tells me how cold it feels outside. Okay, apply a bit more algebra, and we arrive at this equation. We've gone from a pretty picture to a monster equation, but this equation actually gives us what we mean by wind chill, the equivalent temperature in degrees Fahrenheit felt by exposed skin when the air temperature is F degrees and the wind speed is V miles per hour. What may be even more amazing to you right now is that you'll be able to decipher an expression like this and to follow all the steps that led to it within the first third of this series. Right now, the wind is 20 miles per hour, so we plug in 20 for V. The temperature outside is 28 degrees, so that's F. And we discover that the wind chill is 0. That means walking outside right now, I'd feel as though the temperature was 0. And it means that the applications of algebra are as close to home as the weather report in winter. No, you're still watching in simplest terms. I just thought that in honor of my fellow TV hosts, I'd say a word about the how-to approach. This old house will teach you how to build bigger closets or even a beautiful outdoor deck. But the show assumes that you can wield a hammer and drive a nail. And Julia will help you prepare delectable dishes that you never even heard of before. But she assumes that you know how to turn on the oven. Well, for better or worse, there's a sense in which college algebra is about learning how to drive nails and preheat ovens. Our subject in this series is the foundation for many things that you might study in the future. It won't surprise you to learn that college algebra is an essential building block for the further study of mathematics, trigonometry, calculus, and beyond. It might be less obvious that algebra also contains the mathematical skills you'll need to prepare for many scientific, technical, and professional occupations. Now, many of the applications and techniques that we're going to cover are useful and interesting in their own right, so don't get me wrong. I'm definitely not saying that this entire series will only consist of skill-building exercises towards some hypothetical future course. I am saying, however, that the how-to ability that you'll pick up here will serve you well and will be a requirement for many things you want to learn more about. Join me next time when we'll begin speaking the language of algebra in simplest terms.
Annenberg Media. For information about this and other Annenberg Media programs, call 1-800-LEARNER and visit us at www.learner.org.